C++ is an object-oriented language, and consequently, in a C++ program, we are working with objects. Objects are instantiations of classes. A class defines the behavior and properties of objects created from it. Object behavior is implemented with methods, and the object may contain data members of various types. These data members are initialized when the object is created. Initialization is governed by a set of rules. I will discuss these rules shortly. During the lifetime of an object, its methods are called on to perform some tasks, but the object may also be copied, moved, or another object of the same type assigned to it. In this tutorial, I will talk about copy and move constructors and assignment. At the end of the life of an object, the object is destructed and the memory occupied by it is released. This typically occurs when the object goes out of scope, although it may be intentionally deleted if it was created on the heap. Let us begin with asking the question, what is a constructor? A constructor is a method that executes when an object is brought to life. This may occur at the time of declaration, if the object is created on the stack, or when memory is reserved for it, if you explicitly create the object with the new keyword, or preferably with a smart pointer. In a class definition, the constructor appears as a method whose name is the same as the class's name, and it does not have a return type. It may or may not have parameters. If a constructor can be invoked without any arguments, then it is called a default constructor. Now let's run this little program and see what we get. This is interesting. Person objects P1 and P3 were both created with one of the two constructors of the class. So far so good. The constructor initializer for object P3 initialized the member variables as expected. However, P1 seems to have lived for a ridiculously long time. The thing is, when object P1 was created, no value was assigned to the age variable. What we see here is just garbage. How about the designation member variable? It is of type string, and a string is actually a class in C++. The designation member variable was initialized to the empty string by the string object's default initializer. So here is one of the rules of initialization. Member variables of simple types like integer, double, or even pointer are not automatically initialized. Their values are left undefined. On the other hand, when the compiler encounters a member variable whose type is a class, then it calls the class's default constructor. If the class does not have a default constructor, then the compiler will complain. Let me expand a little bit on the initialization of objects. We saw that member variables can be initialized in the constructor using this syntax. By the way, I could also put constants in here. For instance, I could say 75 for the age here, and then the supplied value for the argument will be replaced with this constant. I can also initialize member variables in the body of the constructor, for instance, like this. The age variable now contains the value 27. There are a couple of things to observe here which are not immediately obvious. I am referring here to the sequence of events when an object is created. Member variables are created first, and they are created in the order of their declaration. If there is a constructor initializer, like this one here, then the member variables are immediately, that is, at the time of their creation, initialized with the values of the arguments. However, in this case, where the member variable is initialized in the body of the constructor, then this is actually an assignment, because by the time this constructor executes, the variable has already been created. From this, it also follows that if the member variable was an object with a default constructor, then that constructor would have been already called and the member object initialized before execution reaches the person class's constructor. So in this example, it wouldn't make sense to initialize the designation variable, which is a string object, in the body of the constructor, unless, of course, we want to assign to it a value other than the empty string. But strictly speaking, that's an assignment, not an initialization. Another thing to be aware of is that when you have a constructor initializer with two or more arguments, you might assume that the initialization takes place in the order those arguments are listed. But that is not the case. Regardless of the order of the arguments, the initialization takes place in the order the member variables are created down here, from the first down to the last. Last but not least, the member variables can be initialized in the class definition. I could write this instead. Am I assigning 27 to the age variable here? No, I'm not. This is still an initialization, not an assignment. When you see a type name on the left, you know it is not an assignment. This is another form of initialization I will talk about later, called copy initialization. But first, I want to remove both constructors and comment out these lines. Will this code still compile? Yes, it does, because under the hood the compiler generated a default constructor. So person object P1 could still be created even though I deleted the constructors I wrote. Now I want the person to have a name, so I'm putting back this constructor. Something unexpected happened. The red line under P1 tells me there is a problem. It says, no default constructor exists for class person. It is because a set of rather intricate rules govern when the compiler will and will not generate default constructors. I will summarize these rules after we covered the other constructors. For now, from this example, you can see that if we create a constructor, the compiler sulks and no longer generates a default constructor for us. But that is not the end of the story, because we can force the compiler to create one regardless. What we need to say is this: person equals default. Now the red line is gone, and the program compiles. The next constructor I want to discuss is the copy constructor. One might think that the role of the copy constructor is to allow one to create a duplicate of an object in those fairly rare cases when such a need presents itself. This is certainly true, but object copying occurs a lot more often and it is not necessarily explicit. For instance, every time you pass an object to a function by value, the copy constructor is called on that object. The same might happen with function return values. The copy constructor could also be at work in object declarations. In the following, we will look at examples of all of these. The syntax of the copy constructor is as follows. In the implementation of the copy constructor, every data member of the source object should be copied over to the destination object. In the person class, they would be the designation and age variables. An alternative would be to write a copy initializer constructor like this. To help us see when the copy constructor was executed, I am adding this diagnostic message here. Then here is a function to call to test the copy constructor. Now let's see what we've got. This first line was printed by the original object, and then a copy was made here, and so we got this printout. And this third line was printed by the copy. This P goes out of scope here and gets destroyed. Of course, you don't need to pass an object by value. In fact, it is more efficient to pass it by reference. In this case, a copy wasn't made, so the copy constructor wasn't executed. We can call a copy constructor explicitly. Here the variable Dr. Jekyll is initialized with the already existing person object P. As you can see, the copy constructor was executed. I could just as well write this. Again, this is not an assignment, but a copy initialization. If we don't write a copy constructor, the compiler will silently create one for us. We can also specifically request the compiler to create a copy constructor using a similar syntax as with default constructors. On the other hand, if we'd rather not have a compiler-generated copy constructor, then this is how we can achieve that. Now the object cannot be copied anymore. This way you can disallow passing the object by value. Moving on to assignment now. It probably doesn't come as a surprise that you can assign the value of an object to another object of the same type. You've been doing it already. If not with your own classes, then some built-in types. Consider this example. Here, I declared the string variable s1. It is created on the stack, and its constructor initialized the value of s1 to the empty string. On the next line, I am assigning a string constant to the already existing string object s1. So this is an assignment. On this line, however, even though you see an equal sign here, this is not an assignment. s2 is declared and constructed here. Similarly, s3 is copy constructed based on the value of s2. Lastly, here the value of one string object is assigned to another string object. Let's examine this a little closer. I created a label class with a couple of member variables, a default constructor, a non-default constructor, and a copy constructor. Remember that a constructor is a default constructor when it can be called without arguments. My other constructor initializes the value of the label member variable. Notice that the length member can be initialized from the length of the label string, because by the time this line of code executes, the label string has already been created. If I execute these program statements, this is what I get. Label L1 was created by the default constructor, L2 by the constructor that set the member variables to a meaningful value, and the copy constructor of L3 assigned the same values to its member variables. But we yet to add the assignment operator to our class. It is basically an overloaded equals operator. The if statement tests if the object on the right-hand side of the equal sign is the same as on the left, because if it is, then obviously the assignment doesn't make sense. Okay, so with the assignment operator added, I run another test. Here a new label object, L4, is assigned to L1. The constructor was executed when L4 was created, and then L4 is assigned to L1, and so it now has the same label as L4. My assignment operator is not quite right yet. It works, but it is not entirely correct. As you know, you can assign the value of an integer to another integer and, in turn, assign that to yet another integer all on the same line. Our objects should be able to work like that too. So my assignment operator is going to return a reference to the modified label object. As with the constructors, the compiler will generate an assignment operator for the class automatically if we don't write one. The last constructor remains to be examined is the move constructor. But before turning to that topic, I want to alert you to a potential risk of bugs in a program in relation to compiler-generated copy constructors and object assignment operators. Because we don't write them, we might not be aware of when and where in the code they execute and what they actually do. To illustrate, I created a simple class, Lotto Numbers, which stores a history of winning numbers for each week in a year. The memory for the numbers is dynamically allocated when the object is created. It is a 52 by 6 grid. The numbers variable is a pointer to this grid. The week no member is the current week number. When an object of this class is destroyed, the code in the destructor ensures that memory reserved for the Lotto numbers is freed. Then there is a method to add numbers to the grid and a method to display all the winning Lotto numbers up to the current week. In this example, a Lotto numbers object is created and the winning numbers for the first 2 weeks are added. Looks alright. Now I'm going to make a copy of this object. We've already learned that when an object is declared like this, then its copy constructor is executed. I didn't write that copy constructor, the compiler generated it. These curly braces are scope delimiters. This is the scope for the winning numbers object, and this is the scope for the aCopy object. These objects are only alive within their enclosing scope. I put a breakpoint here to stop the program after the aCopy object displayed its contents and before it goes out of scope, and also here where the winning numbers object goes out of scope. The result looks good. An exact copy was made, or so it seems. Now stepping into the code, this is the destructor of the aCopy object. Let's continue. Now the winning numbers object is about to go out of scope, and its destructor is called. Bang! Memory access violation error. What happened? I'm going to use this diagram to explain. Here we have the numbers grid in the winning numbers object after the winning numbers for the first 2 weeks were added. When a copy was made, the pointer to the grid was copied, but the grid itself wasn't. In other words, the copy constructor made a shallow copy of the object. Now, when the aCopy object went out of scope, its destructor deleted the grid, so the numbers pointer became invalid. Therefore, when the winning numbers object went out of scope and its destructor tried to delete the grid wasn't there anymore. So we got an error. Let us now see what the story is with assignment. Again, it looks good so far, but now I'm skeptical. Let's step through. This is the destructor of the ln object. Continue. Now we are in the destructor of the winning numbers object. A memory access error again. It is actually worse than that. Let me explain. When the Allen object was created at the point of declaration, its constructor reserved memory for the grid. Code in the compiler-generated assignment operator assigned the value of the numbers pointer of the winning numbers object to the numbers pointer of the Allen object. So now they both point to the same grid, and the other grid became inaccessible. An error wasn't raised when that happened. The program continued, and we, users, were unaware of the memory leak. Of course, the same dangling pointer issue still manifested itself. I think you can see by now that not being aware of how compiler-generated code works can cause problems. In these examples, when dynamically allocated memory is involved, we need to write our own copy constructor and assignment operator. I'll add a copy constructor here. It is fairly straightforward. The only noteworthy thing to mention is that in order not to duplicate code, I am calling the constructor here to reserve memory for the data. It is possible to call the constructor of the same class in another constructor initializer, but it is not possible to do the same in the constructor body. That wouldn't work. The assignment operator will be more interesting. Here is the definition of my assignment operator, in the body of which I first check if it is not a self-assignment. Then what I need to do is to free the memory currently occupied by the object, because the current data is going to be irrelevant. We won't need it anymore. The next step is to allocate memory for the new data. And lastly, store the new values in the allocated memory space. Oh, and not to forget the weak new member variable, and to return the new object. Are you happy with this? The program runs and we don't get an error unlike before. But there is a problem. Suppose, for whatever reason, an exception is thrown while the assignment operator is executing. Say here where new memory is allocated. Consequently, the state of the object becomes invalid. We should really make the assignment operator function exception safe to avoid corruption of the object occurring. That calls for an all or nothing approach. What we could do is to make a temporary copy of the new values, exchange the old values with the new, and do this in an exception-safe manner, and then discard the old values. The exception-safe exchange method could look like this. It uses the standard library swap method, very handy for our purposes. Notice the noExcept keyword. Now the code in the assignment operator function can be replaced with this. To understand better what is going on, here is a diagram. The goal is to assign the winning numbers object to the other object I called ln. A temporary object is created, and when its copy constructor runs, we end up with a copy of the winning numbers object. Next, in the exchange method, the ln object is swapped with the temporary object. This simply means the pointers are exchanged, so this operation is efficient. Lastly, when the temporary object goes out of scope, its destructor frees the memory originally occupied by the ln object. As you can see, no dangling pointer and no memory leak. Works fine, no errors. When the goal is to prevent side effects caused by compiler-generated copy constructors and assignment operators, an alternative is to simply disallow them. The syntax to do that is this. Okay, so now we are ready to tackle the move constructor and move assignment operator. To do that successfully, we first need to understand what is meant by move semantics. Move semantics was introduced in version 11 in C++, mainly to eliminate unnecessary copying of objects. A typical example when copying is redundant and will only slow down program execution is when a temporary object is involved. Here I have a couple of functions, one that simply returns a string, a quote, and another that outputs that quote onto the console. In the program I create a string object called quote from the return value of the getQuoteForTheDay function. You know by now that this is not an assignment, despite of the equal sign you see here, but the string object's constructor is invoked here. The quote variable is then passed to the printQuote function. When the printQuote function receives the argument, a copy of it is made and printed out. Of course, we can avoid the copying here if we use a reference instead. However, we still have a variable here that is redundant. We could simplify the code like this. The argument of printQuote is now a temporary object. It is the object returned by the getQuoteForTheDay function, but it is not assigned to a variable. A temporary object like this is called an R-value. The quote variable here, on the other hand, is an L-value. An L-value has a name, in this case quote, and you can take its memory address using the ampersand operator. The L in L-value indicates that it appears on the left-hand side of expressions. There are no prizes to win for guessing what the R stands for in R-value. Technically, the printQuote function as declared here with an L-value reference parameter should not accept an R-value argument. Some compilers might be clever enough and by some magic make it work, but what we are going to do here is to create a function overload for R-value parameters. The double ampersand is an R-value reference. So now I can call the printQuote function with either an L-value or R-value. The compiler will make the appropriate selection. If, for whatever reason, you wanted to call a function accepting an R-value argument with an L-value, then you use the move inbuilt function to cast an L-value to an R-value. Don't be misled by the name. Move does not move anything. I will explain how moving actually works a little later. Here is a trick question. Is this Q here, being an R-value reference argument, an R-value or an L-value? Inside the body of the function it is an L-value, because it has a name. So if I made a call here to print quote, that would not be a recursive call. As you can see, the other printQuote function was called, the one accepting an L-value argument. Having introduced move semantics, we can proceed and write a move constructor at last. We'll do it in the Lotto numbers class. I'll just make a quick change. Instead of reserving memory for the numbers in the constructor, I'll allocate memory dynamically as new numbers are added. I'll explain later why I made this change. The definition of the move constructor is this. From is a reference to the object we are moving data from into the object being constructed. As for the implementation, we can reuse the exchange method. I'll first write some code to test this constructor and then explain how it works. I'm going to pretend that we need to store the winning lotto numbers for a number of years for historical purposes. They will be stored in a vector. This function here will get and return the lotto numbers for the year just ended. In this example, I only filled out the first 2 weeks, but you get the idea. Back here, I create a lotto numbers object by calling the class's move constructor I've just written. I know I will call the move constructor because the getLottoNumber function here returns a temporary object which is an R value. The numbers for year object will be constructed from the winning numbers object returned by the getLottoNumbers function. With this code, I'll add the numbers to my history vector and just print out the history. Let's run this. Yes, the move constructor of the numbers for year object was called, and then the temporary object was destroyed. That's why this destructor executing is printed here. The copy constructor executing is from the pushback method of the vector. As you know, unless told otherwise, the vector makes a copy of the object, and it is the copy that's added to the vector, not the original. So this is our move constructor using the exchange method, and on this diagram I'm going to explain what happened. It's very simple, really. In fact, if you stepped through the code with your debugger, this is what you would see. In the getLottoNumbers function, a lotto numbers object is created and some lotto numbers are added. The object is then returned to the caller, which is the move constructor of the numbers for year object. Here, the winning numbers object appears under the name from. As the numbers for year object is constructed, its member variables are initialized. Then we enter the exchange method where the member variables of the two objects are swapped. The object named other is in fact the winning numbers object in disguise. Then, as execution leaves the getLottoNumbers method, the destructor of the winning numbers object is called. So it is deleted. Notice that no extra memory allocation occurred throughout the entire process. This is why the move constructor is more efficient than the copy constructor. Why it is called move when all data remained in place? Well, ownership of memory was transferred, or if you like moved, from one object to another. So that's the reason, I guess. Remember, I had to make some changes to the lotto numbers class earlier. I am no longer pre-allocating memory for the numbers grid in the constructor. If I had still done that, then the code in the destructor would try to call delete on an array that has already been moved. Before saying goodbye to the move constructor, I just want to take another look at the code here. The pushback method of the vector class also has an R-value reference overload. If I could use that, I would avoid a copy being made. But the numbers for year object is an L value since it has a name. To pass it as an R value is possible by using the move function. Now the move constructor was called instead of the copy constructor. What you need to bear in mind though is that after the move, the numbers for year object will not contain any data. It will still be in a valid state because the number variables have some initial values. When you use someone else's classes, this might not be the case. According to the C++ Standards Committee, The standard library objects would be in a valid but unspecified state after a move operation. To be honest, I don't know what that means. At any rate, when you move an object, it is assumed that you don't need it. Don't reference it afterwards. I could simplify this code even further by getting rid of the named variable altogether. The fewer named variables you use, the more efficient your code becomes. Although it could get less readable, so best to find a happy medium. The next thing to cover is the move assignment operator. The implementation is straightforward. RHS stands for right-hand side. The object assigned to is returned by the operator to allow chaining of assignment statements. Now that everything is in place, let's do a comprehensive test. Stop the video and take a good look at the code and try to determine which constructors will be executing at each program statement. Okay, I'm going to run the program. This is a screenshot with annotations. I hope it all makes sense. To finish off, here is a summary of the conditions under which the compiler generates, or rather does not generate constructors. Thanks for watching. Bye.